Hello everyone, I'm N J Wildberger and I'm here to tell you about this channel, Insights into Mathematics, where I'm trying to map out new directions both for the teaching of mathematics and also the research involved in pure mathematics. So I have a rather unconventional approach to mathematics. I think currently pure mathematics has huge logical problems that are unfortunately being ignored by the professoriate. And one of my aims is to, first of all, point out these problems, but secondly, to map out new directions where we can go and explore mathematics in a healthier, more productive, and ultimately more beautiful and accessible fashion. So before I start, I'd like to give a big shout out to my Patreon supporters whose support and help and advice has really encouraged me hugely over the years. And I'd also like to thank the members of my other YouTube channel called Wild Egg Mathematics Courses for their contributions to that channel. So just a word about me. So I'm a retired math professor. I've been teaching at the University of New South Wales in Sydney, Australia for the last 30 years or so. Before that, I taught at the University of Toronto for a few years, and I taught at Stanford University for a few years before that. And I was a PhD student at Yale University, studying with Roger Howe on quantization and Lie algebra harmonic analysis, and I did an undergraduate degree at the University of Toronto. Okay, on this channel here, Insights into Mathematics, there are a lot of playlists covering a wide variety of mathematical topics. And my main aim is to try to, instruct you on this, but I also want to do it in such a fashion that you are able to avoid the more obvious logical weaknesses that pervade most of current modern mathematics from my point of view. So very briefly, there's a wild trig, which is rational trigonometry. That's essentially the story of a new approach to trigonometry, rather elementary but novel, contained in my book. And then there's wild in algebra, which is linear algebra done in a somewhat more geometrical style as usual. The main playlist is probably the Math Foundations, which is very extensive these days, has several hundred videos, okay, covering a whole range of topics, but all largely concerned with the logical structure of mathematics and how do we actually start doing mathematics correctly. And I think the more recent videos in there where I do box arithmetic, I introduce box arithmetic, which should be especially interesting to all students of mathematics. There's a series on famous math problems, a course at UNSW, differential geometry that I taught, another one, algebraic topology, something a little bit in a different direction, Wild West banking, where I talk about difficulties with the banking system from a mathematical point of view. I'm a Go player, so I have a series on teaching you how to play Go. There's also a major series on math history, which covers the history of maths from early days to modern times, and then also auxiliary series on ancient mathematics and old Babylonian mathematics, this one with Daniel Mansfield. There's a playlist on universal hyperbolic geometry. So this is a new approach to hyperbolic geometry. Once you've understood rational trigonometry, then you're in a position to completely rethink the story of the Poincare disk and the upper half plane, etc., from a larger point of view that connects more pleasantly with 20th century relativistic physics. In the Math Foundations series, there's a sort of a sub-series on Boole's logic and circuit analysis, where we go back to George Boole's foundational thinking about the structure of propositional logic and how ultimately in the 20th century to apply it to analyzing circuits. And there's one where I sort of venture into the social sciences with a discussion of sociology and pure maths. Another one on maths and music. More elementary one where I just talk about K to 6 education and my sort of perspectives on what might be a good way of orienting you to thinking about teaching young people. And then there's a sort of more technical series where I talk about math seminars. Okay, so there's a lot of content. It would take you months to go through it all. But if you are a student of mathematics and you don't mind listening to my somewhat pedantic expository style, Okay, because I want to lay things out sort of step by step. I don't want to have large leaps of brilliance or imagination required. Okay, to me, it's important that the logical structure of mathematics be sort of first and foremost. Okay, you should be able to follow a discussion of something, and it shouldn't require, an IQ of 200 to do so. That's my view. And so I'm trying to aspire to that by laying things out rather concretely and explicitly. There's always the fast forward, speed up video option if you already know some of the stuff. But I think in a lot of these lectures, even if you have quite a bit of mathematical experience, you're still perhaps going to see new things and be experienced to novel points of view that might be enlightening. So you probably think that mathematics is a very tight discipline where everything is pretty well nailed down and we're just working around the edges to try to discover some new things. That's the way I used to think too. But over many decades of teaching and thinking about the foundations of the subject and working in a lot of different areas as a researcher, I've more and more come to the realization that modern pure mathematics is actually very weak logically. And it's not just weak, it's actually almost demonstrably wrong in its assertions and its beliefs in certain areas. And this has huge implications, not just for abstract, convoluted maths research, but also for the education of young people at universities and even into high school. Okay, so that's an important aspect of, I'm trying to move us to a better way of educating students as well as doing more sensible research. So what's the problem? Well, it's really like the emperor's new clothes story, that we have this situation where everyone is pretending that these convoluted abstract theories, which are not bedded down by explicit computational examples, are well and good. So we're all sort of nodding and smiling, and the actual logical structure is missing in the very explicit sense that if you wanted to encode some of these sophisticated theories on a computer, get your computer to understand this complicated paper that's just won some major prize or whatever, then you're going to have a very hard time doing that. Or more precisely, you're not going to be able to do that. So it's only by sort of all of us pretending that things work even though they demonstrably don't, that the subject maintains its equanimity. Now that involves us all sort of keeping our heads raised and nobody's looking down at the foundations. We've all agreed that foundations and basic definitions, etc., that's something we did back in high school or perhaps first years at university. We don't have to bother with that too much. We can just give rather glib definitions and we roughly get the idea, and then we can carry on towards our more sophisticated, abstract results that we want to impress each other with. It's an emperor's new clothes situation. It really is. Okay, and more specifically, what are like the specific points that I think are very serious? So first of all, the foundations of pure mathematics, and I really want to stress that I'm talking about pure mathematics here, not applied mathematics. Okay, so my criticisms are not directed towards applied mathematics. They're doing great as far as I can tell. And they're coming up with hugely important things, which is really driving the application of mathematics to the modern world. It's rather us pure mathematicians and the esoteric things that we're doing that I'm concerned with. Okay, and one of the things that we've done is we've outsourced the foundations of the subject to the philosophers. That's essentially what's happened with the 20th century adoption of an axiomatic system based on certain kinds of set theory. So I talk a lot about that kind of thing in my Math Foundations course. I could talk for hours about that, but that is, I think a main point. It's a little bit like IBM outsourcing, the operating system to Microsoft. Okay, that's not so important. We've got more complicated things and more important things to work on. Well, maybe, but maybe actually it's the foundational basis of the subject, which is ultimately really the most important thing. Okay, that if you get that wrong, then everything that you build on top of it is going to be compromised. There's a mistaken belief that's almost universally accepted, that it's admissible to talk about infinite processes and their completions. So we can think about having some process, maybe an algorithm or something like this, and it's running and it's generating perhaps more and more and more stuff. okay? And we're allowed to think about what happens when we go to infinity, when we complete this process, when the thing is finally done. Of course, it's never actually done. It's sort of by definition a process which is just carrying on going. But somehow we've allowed ourselves this almost religious belief in believing that we're able to sort of fast forward to infinity, bypass all that computation, which requires more and more universes to actually fill up, and get to the final result in quotes. And then that final result, we usually give it a name, maybe a Greek letter like beta. Okay, beta is the result of this infinite process. Then we pretend that this beta is some kind of legitimate mathematical object that can be then used for subsequent equations, subsequent analysis, subsequent logical derivations. Now we take beta and we add it to alpha, which we got in some other stage. Okay, so that kind of thing. So this is endemic in modern mathematics and represents, in my view, a serious flaw. Okay. It's a serious flaw because we're pretending that we can do something that we actually can't do. There's a lot of sloppy and inadequate definitions where people are ultimately really preaching to the choir. So, if you already have a degree in mathematics and, I'm doing something and I say, okay, now we're considering the notion of a function, for example. And you ask me, well, what's a function? And I give you some glib definition. Oh, it's a rule that takes everything of one kind and gives you something of that kind. So some little thing like that, you'll accept that because you already have an intuitive understanding of what that is. But that's different from a definition which makes sense to someone who has not seen the concept before. Ultimately, that's a litmus test for whether your definition is really solid or not. Another way of putting it is that, is your definition so clear and so precise and so unambiguous that you could actually encode it on a computer? That's a very good criterion, okay? And a lot of modern mathematics definitions fail that sort of obvious, sensible criterion. There's a lack of explicit representative examples. Because we're so enamored of these fancy highfalutin theories, which are built on intuition and prior understanding of previous highfalutin theories, it's very hard for us to give concrete, explicit examples of the things that we're talking about. Okay, so it's almost goes without notice these days that we have these big papers full of talking and so on, and if you actually look to see where the examples are, there are almost no examples, or if there are some examples, they're of sort of a kind of a trivial kind, that we just write down some symbols and you don't actually really come back to the definitions and exhibit something that actually satisfies the conditions of your definitions. This, of course, makes learning mathematics particularly challenging for students because, students want to see examples, but we have a massive poverty of examples, especially in the higher levels of mathematics. And there's a preoccupation with complexity, as I've already hinted. It's a highly competitive field. We all want to become famous or whatever and get tenure and get professorships and get grants, etc. So in order to compete in this realm, as I talk about in my sociology series, it's necessary for us to try to present a sophisticated and as complicated persona as possible. We want to impress other people with the sophistication of our results. And so this means that we have a natural tendency to avoid foundational issues, which are rather at a grassroots level, because they are perhaps seemingly too trivial. Okay? And preoccupation with those things might interfere with your career. So these are some of the serious issues that I have, and so I want to move mathematics into a different orientation where we are doing things a little bit differently and where the logical structure is always first and foremost in our minds. So just to give 3 explicit examples of the kinds of issues that I think are obviously problematic. Let's look at real numbers, functions, and topological spaces very briefly. So real numbers are supposedly the modern foundation for analysis and calculus, involving not just the usual integers and rational numbers, but also so-called irrational numbers. And pretty well every mathematician on the planet believes that there really are such things. I don't. Okay, I don't believe it. I think it's nonsense. But anyway, okay, so if we inquire, well, where are these irrational numbers? Certainly in this picture, you see a few integers. Well, we could subdivide these things perhaps and get some rational points. If I ask you, where are the irrational numbers? Well, that's not so easy. So it requires sort of, pretending that you can subdivide one of these intervals sort of essentially infinitely. You can just keep on subdividing, contravening the laws of physics, at least as we currently understand them. Once you get down to the quantum level, you can't keep on subdividing. But in our minds, we pretend that we can. And furthermore, we pretend that we can finish infinite processes. So we can create these little infinite processes where we're going smaller and smaller steps and creating these sequences which don't have rational number limits, and then these sequences then supposedly generate these new irrational numbers. And supposedly there's an arithmetic with these things, which in many places I make fun of, okay, because there obviously isn't. And a good test to see whether I'm right about that is to ask our computer science friends, the people who, say, generate mathematical, computational programs, Mathematica, MATLAB, Maple, etc. They are not able to encode real number arithmetic into their machines. So if we ask for supporting evidence to see real number arithmetic on our machines, we're not able to see that. But nevertheless, we're all supposed to, buy the religion that there is such a valid arithmetic, because there's just so much at stake. Okay, there's so much at stake in terms of the theoretical consequences of having the pleasant properties that such a system would give us if it really did exist, if it really was properly defined, which it isn't. Okay, another example is that of a function, which is a much overused concept in 20th century mathematics. So if you ask an analyst, what's a function? They'll say something like, well, it's a rule that takes an object of a certain kind and gives you an output, an object of another kind. And then you ask, well, what do you mean by the word rule in this case? Well, then they might give you another synonym. Maybe it's a program, or maybe it's an algorithm, or maybe it's a procedure, etc. But you're not really pinning down what's going on. And crucially, you're not clarifying whether you're on the computational side of things or on the choice side of things. Okay, so if you're talking about procedures, then you could be talking about a computational procedure, one for which there's a computer program that you can use to run this procedure. Or maybe more abstractly, you could be thinking about a choice procedure, which involves some, perhaps some creature outside our universe to be making an infinite number of independent choices. It's an axiom in modern set theory that such a thing is possible. Okay, but if we're not actually even distinguishing between these two possible aspects of the definition of function, then clearly our definition is not tight enough. Okay. So here's an example, say sine of x. Well, here's an example of a function that I'm happy with. So here's a function represented by a table, values 1, 2, 3. We're going from the set 1, 2, 3 to the set 1, 2, 3. F of 1 is 2, f of 2 is 3, f of 3 is 2. So it's entirely specified by this table. It's a complete finite procedure. We can see everything about it. We can be happy with this. In contrast, in marked contrast, here's the sine function, just one of many transcendental functions which are used all over the place in modern mathematics. So if I ask my mathematician friends, what's the definition of sine of x? Well, then I very well might come up with this answer. Oh, it's the result of this infinite summation. You take x, and then you subtract x cubed over 3 factorial. You add x to the 5th over 5 factorial. Minus would be the next one. Okay. And you continue like this. And how far do you continue? Well, you just continue to infinity. Okay, whatever that means. Okay, it means something to my fellow mathematicians. It doesn't mean anything to me. But they think that it means something. You continue this to infinity, and then what you get is the sine of whatever the x that you're interested in. Okay, so to me this is sort of obviously not supportable by computation, because we're positing that we can do something that we actually can't do. On a more abstract level in topology, we talk about topological spaces. And typically, there's much more to it, but roughly we start with an infinite set. So we're just allowed to say that. We start with an infinite set. And then we have a bunch of open sets. And in fact, there's open sets are also infinite in number, and any one open set is typically an infinite collection or subset of the original X. Okay, so maybe, you know, there's one open set in red, there's another open set in green, there's another open set in black. And then these myriad of open sets that we have ought to satisfy two crucial properties, kind of a closure with respect to intersections and a closure with respect to certain kinds of unions. So there's ultimately infinite amounts of things to check. And if you've done all that, then you have a topological space. Yes, but this is sort of obviously something that you can't exhibit in its entirety. If X was a finite set, yes, no problem, you could do that, and then you get actually quite a reasonable, interesting potential sort of theory. But the step from the finite to the so-called infinite is one that is not supportable by explicit examples and by what we can actually encode on our computers. So those are three examples. I talk a lot more about those kinds of things in my Math Foundation series. But generally speaking, in all of this channel, you're going to be given mathematics where I try to avoid these kinds of difficulties. So I want to lay out alternative ways of thinking about mathematics. And I claim that in many cases this gives us deeper insights. It opens up new ways of thinking about things, and it opens the possibility for a better understanding and more happy education of young people. So I'm hoping that you will dig into my channel and start exploring some of the things. Make comments, please, and give it some thought. I'm N J Wildberger. Thanks for listening.